And we're live. Okay, so today I want to start by going over some of the homework. This is probably hard to see, so we'll make it bigger. This answer key is on Courseworks under Files and Resources, Answers Key. So the first question was about bowling. This is kind of a Bayesian problem with a discrete, not only data, but also discrete value of gamma. So I think people had a pretty easy enough time during the first few. This was pretty much the same as what we did in class. You can always check whether you made the 11 by 11 table right by verifying that it's non-negative, and then it sums to 1. The expectation and the variance can easily be obtained just by applying the definition. So in the case of the second rule, we need to sum down the columns in order to get the marginal probability of knocking down x2 pins on the second roll. And then we just multiply the sample space by those marginal probabilities to get the marginal mean on the second roll, which is slightly above 1. So you can see already that introducing the gamma is not changing the probabilities or the mean that much relative to what we had previously. But it makes a more challenging homework problem. For the variance, you have to get the marginal probability of knocking down this number of pins on the first roll. Then you have to calculate the mean. And then to get the variance, you have to weight the quantity omega minus mu1 squared by the respective probabilities, sum it all up. You get a slightly different variance from what we got before, or you could do the expectation of the square minus the square of the expectation, should get the same answer. The variance of a Poisson is the same as the mean. Different people had different values of the mean that you were supposed to assume. I'll just use 2.5 below. So it started to get more interesting when we talk about independence. So you're in the next couple of sections, there's going to be 9 frames of bowling. What we did in class the last couple of weeks, we just sort of were thinking about 1 frame of bowling in isolation. Now we have 9 frames collectively, and it's fairly reasonable by social science standards to assume that the frames are independent of each other, because there's no physical reason enforcing dependence between them. You start over with 10 pins at the beginning of every frame. However, within a frame, the 2 rolls are definitely not independent, because how many pins there are to knock down on the second roll depends on how many you knock down on the first rolls. But you can always come up with reasons why something is not perfectly independent. You know, someone might get like more or less confident based on what happens on the first couple rolls, and that affects their probabilities on their later rolls. Another thing to clarify is really when we say these rolls are independent, we mean they're conditionally independent given gamma. So with gamma, you can generate the 11 by 11 probability table. If you know that, then it's basically saying 1 frame doesn't tell you anything about another frame. So that I think people managed to get pretty well. So where people started to have trouble was calculating the posterior kernel. It's pretty much the numerator of Bayes' rule, and then on the next problem, the denominator. So the kernel of a probability function is just, you know, what's left over after you've thrown away any terms that do not involve the random variable in question. And the random variable in question here is gamma. So loosely speaking, we're going to be multiplying a prior by gamma times the probability of the data, or something proportional to that. So we have the kernel of the Poisson PMF here. I've dropped the e to the negative mu term because that's a constant, or otherwise something that does not depend on gamma. So it's legal to drop that to get the kernel function. But the rest of the kernel function, the conditional probability of the data given gamma, here you have to think back to the previous question, which says these frames are independent of each other. And if we have multiple things, in this case 9 frames, that are independent or conditionally independent, more properly speaking, then the probability of them collectively is simply the product of the probability on each frame. And the probability on each frame follows this ratio of Fibonacci stuff that we've been talking about previously, with the slight amendment that you now have a gamma floating around in each of these terms that was, given earlier in the instructions. So you have a probability function for the first roll, a probability function for the second roll, conditional on the first roll. So you have 10 minus x1 in frame I down here. And of course, multiplied by an indicator function to ensure there's probability 0 of knocking down more than 10 pins in the same frame of bowling. And so this is really the key, and what took, I think, a lot of people a while to make the connection there, that if you have independent frames, the probability of the 9 frames collectively is the product of the probability of each of the 9 frames all multiplied together. All right? It's just using the definition of independence across frames. Got it? Okay. So there are even more questions about the denominator. So I wanted to go through this one in a little bit more detail. You didn't have to put this much detail on your answers. But we start with Bayes' law. So a conditional probability mass function, because gamma is discrete, for gamma, conditional on the data and our mu that we came in believing before we saw the data, is equal to a prior probability mass function for gamma times the probability of the data given gamma divided by the marginal probability of the data. So that's just Bayes' law. But because the thing on the left-hand side of Bayes' law is a valid conditional probability mass function in the discrete case, it must sum to 1 over the entire sample space omega, which in this case is all non-negative integers. So the sum, this should be a g here rather than a gamma. I'm inserting g from 0 to infinity. The sum of all that has to equal 1 for this to be a valid probability mass function on the left-hand side. And if you sum the left-hand side and you get 1, what happens when you sum the right-hand side over the entire sample space? 1. Also said right here, the right-hand side of Bayes' law must sum to 1 as well. So we stick g in from 0 to infinity in all the places where gamma appeared on the right-hand side. We're going to sum up the right-hand side. It's also going to be equal to 1. Now, since the denominator piece does not involve the index of summation or gamma, g, none of that, it only depends on x, we can take this piece in the denominator and move it to the left-hand side of the summation and just sum, the numerator piece. Still going to be equal to 1. So if we have, positive thing multiplied by sum of positive things equal to 1, all we have to do is multiply both sides by f of x1 and x2, and we come up with the relationship, the summation of the numerator of Bayes' law is equal to the denominator of Bayes' law. And that's really the key to understanding this question conceptually. Now, in doing that, I can again drop the e to the negative mu term because that doesn't involve gamma. So if I write out the Poisson PMF explicitly, I can pull the e to the negative mu part outside the summation and then divide by e to the negative mu on both sides. And now I have the summation of all this is equal to denominator of Bayes' rule divided by an arbitrary constant, or not entirely. Well, it's pretty much arbitrary in this case. It was specified what mu should be for your problem in this one. So I can either sum the numerator exactly and get the denominator, or I can sum the numerator kernel and get something that's proportional to the denominator. Either way, if I divide the top by the bottom, I'm going to get the same thing for my probability mass function that represents the posterior probability mass function. All right? So if you start with the fact that PMFs sum to 1, it's pretty straightforward from there. Now, when we want to compute what this number is for these particular data, and that's just one of the most important things about the Bayesian approach that's different from frequentism and stuff like that. We're calculating it for the data that we have in hand, not some imaginary population of data that we repeatedly sample from or anything like that. So we load up the data. Person started off with a turkey, then got a 4 and then a 5, so they didn't get their spare, a 9 and then missed, a spare, a strike, and then missed, and then another spare. So these were basically made up numbers, and we want to compute what this piece is over here. So we're going to approximate the sum from 0 to infinity with the sum from 0 to 100, and this, whether it's accurate or not, depends on the context. But in this case, the contributions to this infinite summation become very, very, very close to 0 pretty quickly for small values of mu. And so summing from 0 to 100 is going to be just fine. So I'll use mu is equal to 2.5. All of you had different numbers. We'll just start a denominator at 0 and accumulate it up. So we'll do a for loop from 0 to 100, add to the denominator basically this piece here, but in our code. Sum it all up. After the end of the for loop, we can print out what the denominator is, and it's some number like 3.34 times 10 to the negative 8. And that sounds like a very small probability, and it is, but that is representing the probability of observing exactly these 9 frames of bowling, or some permutation of it, because we assume that they're independent of each other. But there's lots of other combinations that could have happened that didn't, and so the probability of the one that we observed ex ante was pretty unlikely. But they were all, each individual thing that could have happened in 9 frames of bowling is pretty unlikely. Doesn't matter if it's a big number or a small number. When it comes to evaluating the posterior PMF, we just take that fraction, divide the top by the bottom, and now we have our number for the posterior probability that gamma could be this or that non-negative integer. So people had a little bit of trouble with this one as well, but pretty much all you had to do was construct the left-hand side of Bayes' law by dividing the 2 pieces, and then evaluate it at 0, evaluate it at 1, evaluate it at 2, evaluate it at 3. When the cumulative probability of all those added together crosses 0.5 for the first time, that's the posterior median. It's the smallest value such that at least 0.5 of cumulative probability is to the left, and at most 0.5 is to the right. Although if you're looking the other way, left and right are reversed. Okay, so we just have to find the smallest number such that half the probability, at least half the probability, is that or less. So I just wrote myself a function that corresponded to what we did above. This is perfectly valid. However, I just want to plant in your minds now that this is something that a computer can't evaluate terribly accurately if we had a lot more data. So a better way of implementing these probability mass functions and also probability density functions is to work with the logarithm of them. They're always going to be positive numbers, so the logarithm is well defined. And at the end, you know, if you want it in the original units, you just do the anti-log of the probability mass function in log units. Or sometimes later in the semester, we won't even bother anti-logging. We'll just work in log units. And so if you symbolically apply the natural logarithm to this expression in the posterior function here, utilizing the fact that the logarithm of a product is equal to the sum of the logarithms. And so the logarithm of a power, you bring down the exponent and then take the logarithm of the base. The logarithm of a ratio is the difference between the logarithm of the numerator and the logarithm of the denominator, all those sorts of things. So we can get a log posterior by taking gamma, multiplying it by the logarithm of mu, subtracting the log factorial, which has a special function in R that implements that. And then rather than a product over the 9 frames, it's a sum over the 9 frames of the log probability, you know, of the first roll plus the log probability of the second roll. So we get this and then subtract the log of the denominator finally there. So we pretty much get the same thing, but in log units, which a computer is going to be able to evaluate much more accurately. Basically, when you're doing numerical computations, you don't want any number to get super close to 0 because there's going to be underflow, other sorts of inaccuracies. And so instead, if I sum up a bunch of negative numbers, you know, I get like a pretty big-ish negative number, like negative 400 or whatever. And if you need to, you can EXP that at the end to get back to the original units, but doing so in a way where the whole thing is going to be calculated more accurately than if you literally applied the math that I developed previously. So we'll see plenty of opportunities to do that, particularly as we get into writing stand code in April. I just want to emphasize it to you like over and over again until we actually get to that point that you should do probability calculations in log units rather than the original units. So in this case, yours might have been a little bit different depending on what your mu was, but we'll just like while loop that up and it stops the while loop when it crosses 0.5. And we find in my case, the posterior median was 2, which could also be shown by putting a plot of the probability mass function, or at least most of it, for different values of gamma. So we see here 2 is the mode. It's the value of gamma with the highest probability. That's a little bit above 0.25. 1 is a little bit, the probability of that is a little bit above 0.2. So those together are going to be 0.45 or 0.46. And then the probability of 0 is like 0.08 or something like that. So if I add the probability of 0 to the probability of 1 to the probability of 2, I just cross 0.5 in cumulative probability. Consequently, 2 is my posterior median. And like I said before, the probability of any of these numbers falls off quickly. So you can barely even see it by the time we are evaluating 12. We took it up to 100, which is going to be, plenty accurate. In any event, all those like numbers past 100, none of those are going to affect what the posterior median is. All right? Questions about that? Yes?
I'm just curious if there's another way to get the median besides counting up like that until you hit 0.5.
There probably is. Or make a picture. Draw like a million or whatever with these probabilities and evaluate the median. Anything would work there. Yes?
Why is that method not numerically stable?
Oh, if we had, it is in this case because we had only like 9 frames of data. So we were multiplying 9 small numbers together. That's going to be a small number, but it wasn't like dangerously close to 0. If we had 9,000 frames of bowling, then you're multiplying like 9,000 small numbers, and the computer wouldn't be able to, like in floating point numbers, distinguish that from literally 0. But if you do the logarithm of it, then you get like farther and farther away from 0 in the negative direction in log units, and that it has plenty of extra decimal places and stuff to keep track of all that. Sean.
So is the numerical problem the only reason we work with log so much?
Sometimes it's actually simpler to do like mathematically or analytically, because like e's and stuff, they all cancel. So it can make the expression simpler, but there's nothing special about log units. Like probability is what sort of makes sense to the human. So this is definitely like a trade-off that's favoring computational considerations rather than intuition. Yes.
Sorry, doesn't the sign change because you're working with the log of a very small number? So
Yeah, so you just add up a bunch of negative things. And so in log units, some of these probabilities might have been like -30, -40, something like that. Another question? Yes?
Can I use the round cumulative probability equals 0.5 as the condition of loop?
Probably. It sounds like that would be easy to mess up too, but yeah, it's probably, you could get the right answer that way.
No, my answer is different from that.
Oh, you got a different answer?
In my assignment, when gamma equals 1, the cumulative probability equals 0.48.
Uh-huh.
Gamma equals 2, the cumulative probability is 0.74.
Right, so the median would be 2. It's the smallest number such that at least half is equal to that or less. So if the cumulative probability of 0 and 1 was only 0.48, that's not enough. You have to go one more. Other questions? Okay, so the second problem was sort of a Bayes. Oh, and I should also say that, like, okay, here's my plot of the posterior on gamma conditional on the data. And here was my plot of the prior distribution for gamma not conditional on the data. And your eyes probably can't even really distinguish between those two, which is to say 9 frames of data didn't provide a whole lot of information about what gamma is beyond what we already assumed with our Poisson prior. And that is also in part, it has to do with the probabilities in the 11 by 11 table are not very sensitive to gamma. So if gamma is small or if gamma is big, you get pretty much the same thing. Consequently, observing data doesn't give us a whole lot of information to distinguish one value of gamma from the next, above and beyond the information that we came in with this sort of asserted prior that was given there. So in other situations, like, you can make more progress even with only 18 observations. But in this case, it would have taken a lot more data to really shift things that much, unless you had a very ridiculous value of mu, in which case you might have been able to, like, perceive the change as you update your beliefs from prior to posterior. Question?
Is the magnitude how different the data is? Matter, like, if our bowler had, like, blanked out, would that have shifted it, or is it just the number of frames?
Yeah, well, both of those. So yeah, these data were actually generated for a bowler with a gamma of 4. That was the true one. So if it had been like a horrific bowler, then yes, you would have seen different things. Uh-huh.
So how do we interpret this distribution of 0 to 1? Is this the distribution of the bowler scale, like, in the population, or is it the distribution based on this specific?
This same bowler bowled 9 frames and then left without doing the 10th frame is a little bit weird because you get an extra roll if you get a strike, or 2 rolls if you get a strike. So we just cut it out after 9. So for this hypothetical bowler, your beliefs about that bowler, who may not be you, could be somebody else, but your beliefs about that bowler represented by this. So the probability that gamma for that bowler is 3, according to your beliefs, or my beliefs in this case, is like 0.22. And the same, or not the same, but correspondingly for any other value of gamma. So given the data that you saw, this is what you believe about that person's gamma. And there's no bigger population or anything like that. Nothing depends on like, what if we saw more rolls or things like that. Okay, question 2, I'm gonna say is a little bit easier, but in general, dealing with continuous random variables and Bayes' rule is going to be harder. This was one of the rare cases, albeit sort of concocted cases, where you can work through it analytically. So the setup of the problem is you have some random variable x that's uniformly distributed between 0 and beta, but you don't know what beta is, except you know that beta is positive. And one way or another, you have beliefs about beta that are captured by this CDF, which is valid for any value of beta that is greater than m. So m is some value that you have to supply, and m also has to be greater than 0. The other value that you as the researcher have to supply is alpha. And so depending on what m's and alphas you supply, you can get, you know, different shapes to this CDF. I mean, it's going to be bounded between 0 and 1 always, but how fast it slopes up depends on what values of m and alpha you come in with. And since this is an arbitrary problem, I didn't even bother saying what those have to be, but they do have to be such that b is greater than m. Both of those are greater than 0, and alpha is greater than 0. So the first question is, what is the PDF that corresponds to your prior beliefs? That is just the first derivative of the CDF with respect to beta. And that works out, you know, if you simplify it, to alpha times m to the alpha divided by beta raised to the power alpha plus 1. So the PDF, little f, first derivative of the CDF, big F. Hopefully I've said that enough times that you can get through the first one. So then the joint PDF of beta and x, where x is the random variable that generates the data, can just be constructed by multiplying the marginal PDF for beta, which we just worked out, times the conditional PDF for x given beta, which I said was a uniform distribution, and a uniform distribution between 0 and beta has PDF equal to 1 over beta. So we just multiply those two things together, simplify, we get alpha raised to the, or alpha times m to the alpha divided by beta raised to the power alpha plus 2. Okay, so that's our numerator of Bayes' rule. So now we do a similar problem that we had in the first question. How do we get the denominator of Bayes' rule, or something proportional to the denominator of Bayes' rule? So the probability of x irrespective of beta. And this follows a similar logic. We have Bayes' law. In the case of a continuous random variable such as beta, that is going to integrate to 1 over the sample space of beta. If the left-hand side integrates to 1 over the sample space of beta, the right-hand side has to integrate to 1 also. So we have 1 is equal to the integral from m to infinity. Remember, that was the conditions for this to be a valid CDF of the right-hand side of Bayes' rule here. Since the denominator does not depend on beta, we can shift it out to the left-hand side of the integral. And since all that is equal to 1, if we just multiply by f of x, we get the relationship we're looking for, that f of x is equal to the integral of the numerator over the sample space of beta. So often that integral is impossible, but in this case, I specifically chose this one to involve a ratio, and ratios are something that are at least, you know, possible to integrate. Although if you clicked on Wolfram Alpha to do this, like, that's perfectly fine. But it can be shown that the integral of this, or the definite integral of this, is this expression here, alpha times m to the alpha divided by beta to the alpha plus 1, multiplied by the quantity negative alpha minus 1. And I'm going to evaluate that at infinity. So if I put infinity in for beta and alpha was positive, we're going to have infinity in the denominator. So that's just going to be 0. And then I subtract the value of this if I insert m for beta. And in that case, I get this expression here, which simplifies if you take the negative and you switch this piece around here to alpha divided by m times the quantity alpha plus 1. So it's fine if you just cut directly to this, but this is the probability of observing the data irrespective of beta. So if we had a particular data point, it actually doesn't depend on the value of the particular data point. It only depends on alpha and m. Yes?
M and alpha, they're not parameters. So the left-hand side is not a conditional. The left-hand side of the equation is not a conditional.
Oh, here?
Yeah.
Yeah, so oftentimes you'll see Bayesians be a little bit cavalier about keeping around the values that were constants that you supplied to the prior. The point of the numerator or the denominator is that it doesn't involve beta. We've gotten rid of that. So this denominator piece here only depends on stuff that's known, which is x and the value of m that you wanted and the value of alpha that you wanted. The numerator depends on this unknown beta, which we're trying to make inferences about. So we say sometimes the denominator is the constant because it doesn't depend on any unknowns after we've integrated the unknown beta out by putting in, the upper and then putting in the lower and subtracting that to do the definite integral. Yes, as long as you get this integral at the end. That's fine. Okay, yes.
So when you start the question, x has uniform distribution.
That's, yes,
Right.
that's your beliefs about x, yeah.
X given beta is uniform.
Between 0 and beta.
Yeah. So whenever you have a situation like that, are you always going to end up with an answer like this which does not include x for the distribution?
Yeah. So anytime you use a uniform prior and integrate out the unknowns, you're going to get something that does not involve x. But that's only the case for uniform distributions. If it was normal or something like that, then this expression here would involve x somewhere. Okay, so then the posterior or the conditional PDF given a single data point x, all we have to do is take the numerator, divide by the denominator. So that's what we do here. A little bit of simplification gets you to a position alpha plus 1 times m raised to the power alpha plus 1 divided by beta raised to the alpha plus 2. And if we make the substitution, alpha star is equal to alpha plus 1, we get this expression here, which is the same form as the prior that we started with. It's just now we've changed alpha to alpha star, where alpha star is equal to alpha plus 1. So this is another case where the normal distribution for the data and this distribution that you had for the prior, which is actually known as the Pareto distribution, are conjugate with each other. So if you have Pareto beliefs to start with, you observe data, you have posterior beliefs that are also distributed Pareto, but with alpha star rather than alpha as the shape parameter, and alpha star is equal to alpha plus 1. So observing the data bumped up your alpha from alpha to alpha star, and that's how your beliefs changed. So you could do this like one data point at a time for as many data points as you have. Start with a prior, update it to a posterior, use that posterior as your prior when you see the second data point, and use the next posterior as your prior when you see the third data point, over and over again for as many data points as you see. You're always going to stay in the Pareto family. You're just going to be shifting your value for alpha, you know, as you see more and more data, and you're going to get a more concentrated Pareto distribution to represent your posterior beliefs as you see more and more data from this data generating process. So I put some more information about the Pareto distribution. I didn't ask about this on the homework, but you can read through it to like get a sense of like why the variance could be infinite, or you know, some other quirky things like that about the Pareto distribution. Or you can learn more about it just by clicking on this link, which will take you to Wikipedia, which is going to have a page for all popular probability distributions, plus a page for many probability distributions that are not at all popular. All right. So we did one Bayes problem in the case of a discrete gamma, and we did another Bayes problem in the case of a continuous beta. Main distinction between them: for a probability mass function, discrete case, we could do summation of points. In the continuous case, we have to do integrals of area. But in both cases, a probability mass function sums to 1, and a probability density function integrates to 1. And that's really what makes these probability functions special or useful, because you know, something from the sample space is guaranteed to happen if you normalize it to 1. More questions? Yes.
For the question 1, when we calculate the denominator, that's instead of using the arguing function, the Poisson, you give the
I did it by myself.
yes.
Either way is fine. You could drop the constants, not drop the constants. You're going to get this same thing, shape to the posterior distribution.
Write a function or use its function?
In general, the ones that in R are going to be more numerically stable. Like bigger things to worry about. Okay. So moving on to the slides for today. So good news, we're pretty much done with just the math part of probability. We're going to be using probability the rest of the semester, reinforcing the ideas that we've had in these first few classes, but it's going to be more computation and less math. So hopefully by the end of the day, you'll have gotten all the math, but there's a semester-long textbook by Joe Blitzstein and Jessica Wong called Introduction to Probability that is very good. There's a copy in the QMSS office, or I'm sure in the library if you want to check it out. And that textbook has been condensed by one of the TAs for that class into a cheat sheet that is merely 10 pages long. You'd be surprised how much of it we've covered in the first like 5 classes. But if you get that PDF, then you'll have something that you can review. It mentions Markov chains, which we haven't gotten to yet, but this is basically a computational trick to deal with the fact that most of the integrals we encounter, like in the denominator of Bayes' law in the continuous case, are analytically intractable. And so we'll be learning about those. Joe also has videos on YouTube and on iTunes of his lectures for like his basic probability class involving this book. So you could watch those if you feel you need more review. There was also, I put on Piazza a request for someone to take notes for the class. that does not just mean you get to print out what I put on here. You actually have to write, your own notes, integrate them, with it after class. But if you want to do that, you should send your notes that you have so far to the email address on the Piazza post, and there'll be some selection mechanism to determine who has the best notes. And if you win that contest and you keep doing this for the rest of the semester, you get like $250 for notes that you should be taking anyway. So need some people to do that. Today we're going to cover variable transformations, and related to that, how we get the multivariate normal distribution, which is the most important multivariate probability distribution, a generalization of the univariate normal. But before we do that, I want to start with a distribution that is kind of similar to the standard normal. This one is called standard logistic. Its CDF of the random variable z is simply 1 divided by 1 plus e raised to the power negative z. And so how do we get the PDF from the CDF? Derivative. Apply the chain rule one time, you get this expression here for the PDF of z, the rate of change of the cumulative density function at any value of z that's a real number. Again, cumulative density function tells us the probability the random variable big Z is less than or equal to any value little z from the sample space in question. So the standard logistic distribution, it's centered at 0, it's symmetric. So that sense, it's similar to the standard normal distribution. It's a little bit more spread out than a standard normal distribution. But one of the main virtues of it is it has relatively simple expressions for the CDF and the PDF, whereas like the CDF for the standard normal involved that infinite summation and the double factorial and all sorts of stuff like that. This is a little bit easier to work with mathematically. Okay? So if Z has a standard logistic distribution and we define a new variable that's a function of Z, this is x, and x is equal to mu plus s times z, where s is some positive number that you supply, then it's pretty trivial to write z as a function of x, namely x minus mu divided by s. So if you started with x, you could apply this expression, and now you would have z. And so if z is standard logistic, how would we go about getting the PDF for the random variable x? If z is standard logistic. Yes. Okay. Plug z of x into the above. Can you be more specific about where in the above you were going to stick it? So over here. No. Any other guesses? Rosalie?
Put the Z PDF into the X function.
Also no. Adam.
This is not a guess. Parameters for. I mean, it seems like from the homework we have these parameters and then we pretend that we don't have these parameters. So, like, we just pull them out, but we only do all the math. So, like, are they just there to make this harder?
What we're trying to accomplish. Well, what we're trying to accomplish is, okay, if we have a standard logistic distribution, how can we derive the general logistic distribution, which is going to involve parameters mu and s, just like the general normal distribution involves parameters mu and sigma that we set equal to 0 and 1 to get the standard normal. So what we're doing here, if somebody can guess where to stick the z of x, is to derive the general logistic distribution using this method of transformations. Yes?
Can you, I don't, like for normal distribution, linear combination is still a normal. Is that same thing, does the same thing apply there?
Yeah.
So then you can find the expectation of x.
Yeah, so the expectation of z is going to be 0. The expectation of x is going to be mu. But before we get there, how do we get the PDF? Yes. Okay, so we're going to put z of x somewhere, and it's not in the PDF, and it's not sticking the PDF into the z of x function. So what other choices do we have? Stick this function into the CDF, and then do what? With respect to x. Now we're talking. Put z written as a function of x into the CDF for z. So that would be this expression here. I've just substituted x minus mu divided by s. And then differentiate that with respect to x. And that, again, we just sort of apply the chain rule maybe one more time. And we get an expression for the PDF of the general logistic distribution. And that is e raised to the power negative x minus mu divided by s and the quantity 1 plus e raised to that power whole thing squared. So what we have stumbled into is a general principle for deriving new distributions under increasing transformations. That's why I said that s had to be positive here. So that's a minor restriction. So if you just think about this, okay, we're going to stick z written as a function of x into the CDF and then differentiate with respect to x. If we sort of expand that into 2 steps with the chain rule, we know that if we differentiate the CDF with respect to z, we get, if we differentiate a CDF with respect to its random variable, we get a PDF. So, you know, we differentiate this expression involving z of x with respect to x. That is the PDF of z multiplied by the derivative of z of x with respect to x. And then we're just going to, you know, plug in z written in terms of x. So there's no actual z that appears. It's just the expression involving x that is equivalent to z. So general principle, when you're doing a transformation, it's the PDF written in terms of the original variable, or the original variable is substituted out and you have an expression involving x, which is the variable that you want the PDF for, and then multiplied by the derivative of the transformation from x to z. All right? So the reason why this works is the CDF tells you, you know, what's the probability that something is less than or equal to this. And if I do a monotonically increasing transformation to get into that, then the probability that x is less than or equal to little x is going to be the same thing if I just map from x to z, little x to little z. So we have a valid CDF here involving x, and we just need to differentiate that with respect to x. Question? Yes? It does not have to be linear, but anything monotonic is going to be pretty simple. Okay. And I have more practice with that. Let's say z is distributed standard normal. and x is a function of z, namely the function e raised to the power mu plus sigma times z, with sigma being greater than 0. What is the PDF of x, where x is going to have a sample space of the non-negative real numbers, because the E transformation is only positive? So how would we apply the general principle that we just got through learning to figure out what is the PDF of x? Yes, and that would be
log x minus the over sigma.
yes, I think. Okay, so we're going to have to write this substituting away z and putting an equivalent expression in terms of x. Okay, then what do we do with that?
Write the PDF of the standard normal distribution.
PDF of the standard normal distribution in terms of x. And then the last step is to, can I get a multiply by the derivative of
X.
Same
Oh,
thing.
in terms of x.
c with respect to x? So as Nigel pointed out, the inverse function z as a function of x is the log of x minus mu divided by sigma. Stick that into the standard normal PDF, except rather than writing z, you put what z is equal to in terms of x. Multiply by the derivative of z with respect to x. And the derivative of log of x is 1 over x. And then we got a sigma in the denominator there, so we got to have those pieces. And if you're lacking confidence as to whether you did this correctly, you can simply write an expression over here for this thing in R and use the numerical integrate function over the sample space of x, and it should come out as, which it does in this case. So we know that we've done it right. Otherwise, we would know we've done it wrong. So we can manipulate a PDF in one variable to get a PDF for another variable where the second variable is a transformation of the first, in particular, a bijective transformation of the first. All right? You might wonder why there's like 500 distributions on Wikipedia. It's because there's like 3 distributions and then 497 that are transformations of those 3. Multivariate CDFs, PDFs, and expectations thereof. So if x is a vector of real numbers, let's say, continuous random variables, then we can think about the CDF of this random variable x as the probability that the first random variable x1 is less than or equal to little x1, and big X2 is simultaneously less than or equal to little x2, and big XK is less than or equal to little xk, where we supply the values of the little x's to evaluate this CDF at. So we've sort of generalized this idea of a univariate CDF to a multivariate CDF, which involves all these inequalities holding simultaneously. What's the probability of that? Consequently, we can go from the CDF in the multivariate case to the PDF by doing what's known as the total derivative. So here we have a CDF. It's a function of the vector x. X has k elements to it. So what this expression here means is we take big F differentiate it with respect to the first x variable. That's going to be a new function involving like all the x's. We differentiate the new function with respect to the second x variable. We're going to get another function. Differentiate that function with respect to the third x variable. You get the idea. So in the end, we're going to be differentiating k times. If x has k elements to it, that is the PDF of the multivariate random variable x in the abstract. Of course, we can. It is also true. It's a little bit misleading to say this is equals. I mean, it is equal, but it's a completely different way of understanding the PDF. We could write the PDF for the multivariate x as the marginal PDF for x1 times the conditional PDF for x2 given x1 times the conditional PDF for x3 given x2 and x1 times the next x conditional on all the previous x's up until we run out of x's, which would be k. So that is another way of getting at an equivalent expression to a PDF for the multivariate x in general. There's lots of multivariate distributions, but really we only use like one or two. But in general, that's the idea. By miracle of calculus, you could go from the PDF to the CDF, start with the PDF, integrate it with respect to x1 over like, you know, from negative infinity up to little x1. That's going to be some new function. Integrate that function with respect to x2. You're going to get a new function. Keep going till you run out of x's and you get the CDF. In general, these multivariate CDFs, we're never going to be able to write them in convenient analytical forms. So this is just like a way of thinking about the CDF. You never are actually doing a k-variate integral. Conceptually speaking, if we want the expectation of a function of x, that function being g, we take g, multiply it by the PDF, integrate over all the elements of x, we get the expectation of some scalar g function of x. In particular, one of the most important expectations is the expectation of x, which will be written with boldface mu. So the expectation of a vector is equal to a vector of expectations. So mu consists of mu1, mu2, up to mu k. Another expectation, which is a little bit harder to wrap your heads around, is the expectation of the function quantity x minus mu outer product. So the expectation of the outer product of the quantity x minus mu, where outer product is quantity x minus mu times quantity x minus mu transpose. So that is going to be a matrix of size k by k. So this expectation is going to result in a matrix known as a variance matrix, a covariance matrix, or a variance covariance matrix. 3 words, same matrix. So named because this matrix contains variances and covariances. So when we learned last time the outer product of a vector, it fills up a matrix with all pairwise multiplications of the elements of the vector. So in the first top left here, we have the expectation of x1 minus mu1 quantity squared. and the expectation of x1 minus mu1 quantity squared is otherwise known in the univariate case as the what? Variance. So all down the diagonal of this k by k variance matrix, covariance matrix, or variance covariance matrix, we have the expectation of x subscript whatever minus mu quantity squared, which is going to be the variance of that scalar element x in the vector boldface x. So all along the diagonal of a variance covariance matrix, we have variances. So what do you think we have in the off diagonal elements of a variance covariance matrix? Covariances. That being the expectation, let's say this one, sigma 1, 2, that is the expectation of x1 minus mu1 quantity x2 minus mu2, which we defined previously, like last week, as the covariance between two variables x1 and x2. We can generalize that to the k-variate case and put the covariance between all pairs of elements in the x vector into the triangles of a variance covariance matrix. And because the covariance between x1 and x2 is the same as the covariance between x2 and x1, this variance covariance matrix is symmetric, which is to say it is equal to its own transpose. We could switch the row index and the column index for all of these, and we would get the same matrix, or a matrix with the same numbers or symbols in it. So a variance covariance matrix is symmetric. Got it? So this is for a general multivariate distribution. The multivariate normal is a special case of this, which we're working our way towards. Once we talk about multivariate transformations. So if z is some vector of k random variables that are continuous, and z has a CDF, capital F, which, as I said before, can be written as the total derivative of the CDF, differentiating with respect to all those z's. And let's suppose that x is also a vector, and it is a vector that is a function of the vector z. And further suppose this function, which is from the real numbers in k dimensions, that's what z is, also to the real numbers in k dimensions, that's what x is. So if x is some function of z, how would we go about getting the PDF of x? Yes?
Should that be PDF of z? Because that's not the CDF of z.
This is the CDF of z. Oh, yeah. That should be little f. Right. So it has this PDF that is written in terms of the CDF, but it's differentiated k times. Yes. That should say PDF, that should be little f. Okay. But the question is still the same. How do we get the PDF of x? I'll fix this when I upload it later. If we know the PDF of z. How did we do it in the univariate transformation case? Several times. Tad. Write the PDF of z, but put it in terms of what z equals, which is some function of x. And then after that, we're going to multiply by
The derivative of z.
derivative z with respect to x. So it's more or less the same thing in the multivariate case. The PDF of x is the PDF of Z written in terms of X. And then there's basically a massive chain rule thing on the derivative, for the mapping from X to Z. So by massive chain rule thing, specifically, I mean the determinant of the Jacobian matrix, also named, I believe, for Jacob Bernoulli, the namesake of the Bernoulli distribution, also the namesake of the Jacobian matrix. Jacobian matrix is a matrix. In this case, it's going to be K by K that contains all the partial derivatives of the Z's with respect to the X's, for all combinations here. So in the first column, we have derivative of Z1 with respect to X1. Below that, the derivative of Z2 with respect to X1, all the way down, again with respect to X1. Second column, we have the derivative of Z1 with respect to X2, derivative of Z2 with respect to Z, etc. So we have this matrix called a Jacobian matrix that has all K squared partial derivatives of the Z's with respect to the X's. Given that Jacobian matrix, we merely need to calculate its determinant. I've given up trying to explain what a determinant is. However, we will only work in this class with determinants of triangular matrices. So like, one triangle of this is all zeros, in which case the determinant is relatively easy to calculate. It is simply the product of the diagonal elements of the matrix that you're taking the determinant of. So for a triangular matrix, which includes the diagonal ones, the determinant is the product of the diagonal elements. And we can see that this is a generalization because if K is 1, then there's just one derivative in the Jacobian matrix, like it's 1 by 1, which is to say a scalar, basically. And so then we'd just be multiplying by the derivative of Z with respect to X, if there's just one Z and one X. So this is a generalization of what we managed to do before. A little bit more complicated because there's K squared derivatives and this determinant thing, but same general idea. Use the PDF of one thing that you ostensibly know to get the PDF of something else, which you can ostensibly figure out. And we're going to do that for the multivariate normal distribution after we practice one more time in the univariate case. So if Z is standard normal, univariate, and X is a function of Z, namely the function mu plus sigma times Z, with sigma being positive, what is the PDF of X? Shorter way, longer way, don't care. What is it?
It's a normal distribution with the mean of mu.
Okay. So maybe I should have said, how did you arrive at that?
Because in the case of a normal distribution, any linear transformation remains normal.
Yes. So that's a theorem that's actually implied by the mechanics of the transformation that we've done now like 4 times today. So again, what are the process by which we arrive at this true theorem? That if you rescale and shift over a standard normal, you get a general normal? Right, Z in terms of X. Okay, so write Z in terms of X, stick it into the PDF of Z, multiply by, okay, in this case, Z in terms of X would be?
X minus mu over sigma.
Yes. So if Z sub K is standard normal, and moreover, there's multiple Z's, but they are independent of each other, and they are all standard normal, and we collect them into a vector boldface z, and x is a function of z, namely the function mu vector plus L times z, where L is a square matrix that is lower triangular and whose diagonal elements are all positive. What is the distribution of x, or what is the PDF of x? How would we go about figuring out what the PDF of x is? How would we start the process of figuring out what the PDF of x is? Write the vector z in terms of x, which would be what? L inverse times the quantity x minus mu. So once we have z in terms of x, what are we going to do with it? Stick it in the PDF for z. And then what are we going to do? Multiply by the determinant of the Jacobian of the transformation from x to z. So we got step one, L inverse times the quantity x minus mu. Step two, we need to figure out what all those partial derivatives are. So you may have not done that much multivariate calculus, but if you had to take a guess what the derivative matrix of z is with respect to x, if z is equal to L inverse times x minus mu, your first guess would be it's pretty much the same thing as in the scalar case. L inverse. So the Jacobian matrix is L inverse. And like I said, for a triangular matrix, the Jacobian, the determinant of that Jacobian is the product of the diagonal entries. And also, the diagonal entries of L inverse are the reciprocal of the diagonal elements of L. So running a little bit short on time here, we'll zoom through the remaining steps. We stick z of x, written in terms of x, into the PDF for z, multiply by the determinant of L inverse, which is, the same thing as dividing by the determinant of L. So what is the PDF for z if z is IID standard normal? It is merely the product of k standard normal PDFs written in terms of z. So here's the standard normal PDF. If I have the product of those and it involves e, and z is up here in the exponent, I can write that with a little simplification, e raised to the power negative 1/2 sum of squared z's, just using like the rule for products of exponents is the exponent of a sum. Sum of squares of z, I can write in terms of a vector z transpose times z. So this is the form of the PDF of k independent standard normals that I want to stick my expression for z in terms of x into, that being L inverse times the quantity x minus mu. So substitute that. I have L inverse quantity x minus mu over here, and the transpose of that. Transpose of a product is equal to a product of a transposes in reverse order. We learned that on Tuesday, so I'm sure you remember. And we're going to divide in here by the determinant of L. So this is one form of the multivariate normal distribution. However, it's not the form of the multivariate normal distribution that you tend to see. What people equivalently do is make the substitution sigma is equal to L times L transpose and write the multivariate normal distribution in terms of the mean mu and the variance covariance matrix sigma. So that last bit I had to run through a little bit quickly, and there's still one more slide, which we'll pick up next week. But the general process that I've tried to like explain today is that almost all the multivariate distributions, including the multivariate normal, are derived by taking some univariate distribution, k independent elements that are independently identically distributed according to some univariate distribution. The product of them is some multivariate distribution, and then you apply some function of these IID things to get a new random variable that are not independent of each other because the transformation induced dependence between them. And then you have to work out what the PDF of X is starting from the PDF of Z. So that's where pretty much all multivariate normal or multivariate distributions, how they came into being, is transformation of IID univariate random variables. Okay, so that's plenty for today. We'll have plenty for next week too, but we're starting to get into sort of less math, more computation, more applying Bayes rule, less toy problems, things like that.